Ladies and gentlemen, welcome to this pair distinguished lecture today. And today we have a very distinguished professor, also the Vice Chancellor and President of the University of Surrey to be here. And before that, I'd like to invite Professor Chris CHAO to give an introduction to our distinguished speaker. So welcome, please.
Ladies and gentlemen, good afternoon. It is my pleasure today to introduce our very distinguished speaker, Professor Max Lu, President and Vice Chancellor of the University of Surrey, UK. Professor Lu is the first scholar of Chinese origin to serve as the president of a British university, which is not easy. Previously, he was Prof and Senior Vice President at the University of Queensland, Australia. From the end of May, he will take up a new role as Vice Chancellor and President of University of Wollongong. I understand that he will be leaving for Australia very soon. So in the scientific arena, Professor Lu is an internationally acclaimed chemical engineer and nanotechnologist. So this is why today I'm noticing that we have quite a number of friends who are in chemistry, chemical engineering, material science from other universities also joining us here. Thank you so much. His main research interests include absorption and catalysis of nanoporous materials and their applications in clean energy and environmental technologies. He is a double highly cited researcher in both material science and chemistry for many years, the author of more than 600 high-impact journal papers, and the co-inventor of more than 25 granted international patents. Professor Lu has a reputation for engaging business and industry in productive partnerships. In an interview, he once remarked that our fast-changing world requires us to be adaptive and agile in order to make the change we want to see. However, we need to collaborate and work together to be stronger in realizing possibilities and minimizing risks. Over the years, Professor Lu has consulted extensively to industry and government and has served on numerous advisory and review boards. He has also forged closer ties between the University of Surrey and industries and public sector agencies in different countries, including Chinese giant Huawei and Singapore's Agency for Science, Technology and Research, A*STAR, in areas of 5G, 6G innovations. Professor Lu is dedicated to changing lives and shaping a better society through his transformative leadership in academia and the public sector at large. He is a fellow of many prestigious professional academies and societies, and he has been awarded with numerous awards, including a Medal of the Order of Australia for his distinguished service to education, international research, and to Australia-China relations. Without further ado, ladies and gentlemen, please join me in welcoming Professor Max Lu. Thank you.
Thank you very much, Professor CHAO, and I would like to thank Professor Chen for the honor to be here. It's great to be at PolyU. This is my third or fourth time to visit this wonderful university. It's great to see so many familiar faces, friends, and in fact, my mentor, Professor Mai, also here. It's just wonderful to be here, and then great to meet many colleagues from chemistry and chemical engineering, material science. So without further ado, let me just start this lecture. I mean, Professor CHAO mentioned, I think we live in a rapidly changing world. It's a very complex world. I'd just like to highlight a few things. I don't intend to talk about other topics, but just mentioning, technologically, in terms of the science and technology, we are experiencing the most rapid advances in the last decades, 2 decades maybe. So climate change is one of the great challenges for humanity, and mainly because in the last 5 decades, the man-made greenhouse gases, the increase in sea temperature has been dramatic. So that's been recognized as one of the great challenges, which is to do with, of course, the use of fossil fuels, and therefore the topic of today is to address the clean energy future of our society. Aviation space exploration, of course, many experts here who are dealing with aerospace materials, you recognize there's a race now, race to Mars, from Elon Musk's SpaceX. Of course, CERI has a long tradition of small satellite. In fact, it's the cradle of small satellite in the world. The Wright brothers to Neil Armstrong's landing on the moon took 66 years. However, in the recent decades, the acceleration in materials and in aerospace and of course, in space has been dramatically accelerated. In terms of biology, Human Genome Project took about 13 years, costing $3 billion. But now you can do a whole human genome within an hour and cost only about $150. Of course, digital, we're living in an AI era. This is the digital revolution is accelerating, not by years, by months. I think you can see the scorecards of all the generative AI. So that is actually also exacerbated or complicated by the social and geopolitical changes, from Brexit in Europe to Trump first. Now we are experiencing the second term of Trump administration, of course, the Ukraine war. So all of this sort of a titanic shift of geopolitical actually affecting a lot of policies, trades, as we're experiencing the trade war. So all of this actually require us to think more innovatively. How are we going to address the challenges that we have, whether it's energy or health or in societal terms. So that's why, as scientists and engineers, we look to technological solution more, how are we going to make a contribution. And therefore, if we look at the challenges, so this is the late Rick Smalley, the Nobel Prize winner who discovered the bucketball. He made a Congress hearing and talked about the humanities. This is at early 2006, 2007. So he was talking about the top 10 challenges for humanity. Energy and climate being the number 1. You can see on here, this water, of course, water resources scarce, food security, environmental degradation, pollution, and poverty. And then go down the list, the denominator is population growth. Of course, population growth underpins a lot of other social issues, aging, for example, as well as many other problems such as health diseases. And education, the lack of education is another challenge. But today I'm going to focus on the energy and climate. As you have probably heard the term net zero. The net zero world we wish to be in is largely to do with decarbonization of our energy structure. So energy, we traditionally rely on the fossil fuels. Now, gradually, we need to look at how we're going to decarbonize. Okay, this on the left-hand side of the chart, you can see the wood is carbon, almost 100% carbon, and a bit of hydrogen. And then coal, oil, you can see eventually hydrogen is just the cleanest energy carrier. It's not an energy source per se, but then through this so-called hydrogen economy in the future, I mean, we're now just at the beginning of the hydrogen economy. Of course, the hydrogen infrastructure, as I'll talk through this talk, you see very clearly is lacking. Therefore, we need to invest in the infrastructure, including the production and storage and transportation of hydrogen, and as well as utilization, and gradually really replace the fossil fuel through renewable energy sources, and then with hydrogen as the cleanest carrier. So they will have a major role to play in transportation, aviation, shipping, and of course, household heating, as well as many other sectors. So this graph shows the hydrogen industry currently exists. So you can see that at the bottom part, you can see the traditional hydrogen production from fossil fuels. And basically those chemists in the audience would know this is the very conventional reactions. So you can reform the fossil fuel into hydrogen. Of course, you have a carbon. You have to look after the carbon, how to sequester the carbon, capture and sequester. And the renewable energy, of course, is through electrolysis predominantly at the moment. And the hydrogen can be stored in different medium. Hydrogen can be stored in methanol, for example, in ammonia, and in hydrogen itself. So different forms of storage, I'll talk about that later, and then distributed. If hydrogen distributed through the existing infrastructure like natural gas pipelines, and that is also one of the transportation route. And of course, the utilizations and use. So this is the ecosystem. And the US DOE, this is quite a few years ago, I think it's about almost 10 years ago, there was a roadmap developed by the DOE talking about, how many decades it would take for the world to really build the infrastructure and then roll out the hydrogen in a very significant proportion. So I think the definitions is around this time, 10 years ago, is that when the world has about 40% of the energy is carried by hydrogen as the vehicle, as the carrier, the vector, then you probably say, oh, we are in the hydrogen economy. So you can see the roadmap for the R&D. So we are now in the expansion of the infrastructure phase. That includes the production, and of course, there are a lot of technological challenges in the production, and also storage and transportation. So at the moment, we are here, so approximately. And in a few years' time, there'll be more investment, there'll be more progress in terms of many of the bottlenecks. And therefore, by 2040, I think if everything goes well, there will be the onset of the true hydrogen economy. The demand predicted by IEA is very conservative. It's going to 2070. You can see that by 2070, the world economy probably have about 14%. This is very conservative in my view. I think the rate of development, the advancement, the advances in industrialization, in terms of investment, technology development, is double the rate. So this is something that's projected. I think in terms of the sectors, they are accurate. So shipping is going to be the biggest use of hydrogen, then aviation and road transportation, and then household use and commercial use. Right. Of course, hydrogen has already been used in chemical industry for many, many decades, in fact, centuries. But this is a projection very conservative. Now, you might ask why you label the hydrogen as green. Hydrogen doesn't have any color, but this is metaphoric. So brown hydrogen is the byproduct from the existing industries, refineries, for example. And then, of course, the fossil fuel by reforming, cracking fossil fuels, you can obtain hydrogen, but you call that hydrogen is gray hydrogen without looking after the carbon. But if you capture, sequester carbon, then this has become a blue hydrogen. Well, it's called blue hydrogen. And then green hydrogen is the hydrogen produced from purely renewable energy, such as wind and solar. So just to give an idea, 1 kilogram hydrogen will give you 1 day's use, a nominal household in American standard, big houses. So it's about 33.3 kilowatt hour sort of energy. That's what hydrogen, you can drive in a normal passenger car for 1 kilogram hydrogen about 120 miles. So depending on the size of the car, of course. And therefore, for a normal driving range now we have today for petrol vehicle, you need about 5 kilograms. So minimum 5 kilograms. Just bear that in mind when we talk about hydrogen storage later. I probably skip this. The take-home message from the techno-economics analysis of hydrogen production is that it varies from country to country because the electricity cost is different. But the second message is the Chinese is the best in producing hydrolyzers. Because if you look at the world, the market of hydrolysis or the hydrolyzers, 75% is supplied by China and they are the cheapest. And if you then have a cheaper electricity, of course you have cheaper hydrogen. At the moment, the hydrogen from renewable energy costs typically about $5 to $6 per kilogram. But the US DOE target is $2 per kilogram. So this is, in order to industrialize, it depends on the context of the industry. This is what this slide tells you. I won't bore you this, many chemists here. So this PEM, which is proton exchange membrane, there's anion exchange membrane electrolysis process. And this is very basic electrochemistry for electrolysis. And the cost of the whole hydrogen production largely depend on two factors. One is the equipment, which is the electrolyzer, majority of the cost. Currently about 50% or 60% is the electrolyzer. And then therefore the Chinese technology is very, very competitive because it's the manufacturing en masse and also the cost of electricity. So if you reduce the cost of these two components, you can actually reduce the cost of the hydrogen production per kilogram. This is a busy slide. I just want to illustrate the many types of electrolysis. And of course, depending on what the mechanism, the charge carrier, for example, if it's alkaline based, which is now the predominant technology, which is called the traditional alkaline electrolyzers that the Chinese manufacturers produce, and then proton exchange electrolysis and the oxygen ion exchange electrolysis, which is a high temperature. So if you work in ceramics and you're probably familiar with solid oxide fuel cells, and the reverse is the electrolyzer. But there are many technological challenges in terms of course, the limitation of the traditional liquid, conventional liquid alkaline electrolysis is the efficiency is pretty limited to maximum about 65 to 70%. And if you actually look at high temperature, you can go theoretically up to 100%. But then you have a lot of engineering challenges. So the ceramic material, those of you working in this area, has a lot of mechanical integrity issues and thermal property issues when you actually apply this for a long long period of time. So there are many research groups working on high temperature because they are not commercially available. This is more at the lab scale. But there are also demonstrations, but there's no mass production of high temperature electrolyzers. But in terms of the solid alkaline and the anion exchange and then proton exchange, membrane-based ones, and lots of commercial products now, the cost is still quite high compared to the conventional alkaline-based liquid electrolyzers. So therefore, it's actually looking to the future. We're not satisfied with this electricity generation, let's say PV from solar to electrolysis to produce hydrogen. We look towards solar hydrogen, direct hydrogen production in the future. This is the holy grail. So this is why many researchers, I think Professor Yu is here, he's the top expert in photocatalysis. So it's, you look at whether it's distributed or centralized hydrogen production. You know, you're moving towards direct hydrogen production. So for example, you can see that the solar thermal chemical hydrogen production or photoelectrical chemical production, you know, so the long-term goal is to produce this on a larger scale. Of course, high temperature electrolysis is one. You know, the bubble should grow bigger, but in the long term, they should dominate the hydrogen production in terms of systems. Okay, so in that regard, I put this slide to illustrate the progress in photocatalysis, in photoelectrical electrochemical production of hydrogen. So practically at the moment, all the PECs and photocatalysis only give you about 1 to 2%. This is direct solar to hydrogen efficiency, right? But in terms of industrial scale, you need about 10% to reach the viable range, which is in the middle here, so 10%. So a lot of the photocatalysts actually moving towards, you know, 5%, right? This is 2% and then moving up. You know, if we reach 10%, and there you can have the scale up and in a very sort of economically make a viable the production. So this is where we've been working on. I think many experts in this room look at the photocatalysis. It's really the direct photo to hydrogen conversion using a semiconductor nanoparticle. This is all started by Fujishima in 1972, his first master thesis, right? His master thesis actually published in Nature, you know, talking about the titania as a photocatalyst. That's the first serious paper that was published. And then, of course, the whole field is, you know, is burgeoning now with lots of scientific publications. But still, in terms of innovation, there's lots of gap. So the efficiency is really the product of the light harvesting efficiency, the absorption for light, and most of the time semiconductors, you know, narrow band sort of the catalyst can only utilize sort of a UV range of energy. Of course, there are many researcher groups developing the whole solar array, the solar photocatalyst, including our work. The charge separation transfer efficiency, as well as surface reaction. No, there's a redox reaction on the surface. So this is the basic mechanism. We have been doing a lot of fundamental work and published tons of papers. So predominantly, we look at how to optimize the three important areas. One is the electronic structure of this photocatalyst nanoparticle. And by optimizing that is to optimizing the photon absorption, the absorbance, the redox potential, the mobility of the charge carriers. And then you can also look at how to really enlarge the surface area, the surface reactivity, as well as the crystal structure. We determine the diffusion in the bulk of the particle. There's also the charge transfer, the active side, if you use this photocatalyst for chemical reaction. So this is quite a number of years ago, we published this series of papers on the crystallization, how to control the crystal facets, and then the reactivity and the diffusion. So the method we look at it, the three predominant methods or approaches. One is heterostructuring, and second is doping, and third is crystal engineering. So by doing the doping, you change the interfacial atomic structure, and you're going to then enhance the carrier transfer. And by looking at the doping different elements, inorganic elements mostly, you can change the surface potential size, the surface reactivity. And of course, crystal engineering can control the crystallinity and the bulk diffusion. So there was a paper published in Nature where we look at the anatase crystals, how we can control the different facets, the active side, which is the 001 facets, which is not stable. So Michael Grayson from Lausanne actually predict this, published in 1998, a paper in Physical Review Letters, to predict this size can exist, this surface can exist, if you can have some method to stabilize it and to grow preferentially 001 facets and not the 101 facets which inherently exist in anatase crystals. So we did this for the first time, and we achieved 47% stable 001 facets, which is normally from 5%. Now it's to 47%, and later there's a number of papers we published. We can demonstrate the crystals are not exactly nano sized, but it's micron sized. We can achieve 90% of 001 facets. And of course, in order to enhance the efficiency for hydrogen production from say 1 to 2% to 10% is not easy, because the physicochemical processes happens at different length scale and different time scale, from femtosecond to second in terms of the photon absorption, then charge carrier separation and transfer, as well as the surface reaction. But if you have biomass in the liquid, right, in the water, and of course biomass can act as a precursor for hydrogen production, it's even more complicated, because on the surface, this chemical reaction, the transfer of chemicals on the surface, absorption and reaction will take minutes. So you have this length scale, different scales from the electronic structure to nano, and then to this reactor scale, and then time scale. So you have to really understand which step you want to optimize. So this is why lots of studies so far that has focused on the optimization. But there's another approach. Another approach is to really couple the photovoltaic with the photoelectrochemical process in tandem together, so you minimize the losses of the energy. So this is one of the work my former student, Liu Gang, who's now director of one of the Chinese Academy's Institute of Metals Research. He did this beautiful work a few years ago. He actually combined the cold catalyst is nickel and iron oxide hydroxide as the cold catalyst with the dual anodes coupled with perovskite PV. He actually can achieve, I think, 6% or 6.5% in terms of direct solar to hydrogen production. And this is very encouraging. And now I think a lot of people repeating this work also achieve about even 7%, right? 7%, getting closer to the 10%, which is a commercially viable approach. Now, I think I talked enough about hydrogen production, but I think in terms of the infrastructure, the bottleneck is storage. As we all know, when you you can produce hydrogen economically, effectively, but you have to store it, you have to transport it, right? At the moment, I think many people know that a lot of buses running on hydrogen fuel cells use a compressor tank. So compressed tank can go up now with all these people who are expert in structural materials, composite, carbon fiber. You can go up to 700 bar, and you can compress 5 kilograms in a small tank. You can use that. But I think the cost of that container, the system cost, is still very high, number one. Number two, psychologically, people associated with high pressure with safety risks. People don't want to carry a bomb at the back of the car. So therefore, to search and to continue to do research on low pressure hydrogen storage and safe, well, I think the high pressure is also safe in my view, but I think perception-wise, safe materials to store hydrogen to meet the needs of transport, particularly cars, is a very important topic. So we've been working in this area for a long time. So this is an old review, more than 20 years old, but still very insightful. If you look at this Alex Zutel's review, of course, the top, this is the Ragon plot, the energy density, specific energy in the system. Of course, you have diesel, petrol, this is the fossil fuel, they have the highest energy by both measures. And coal, so of course you can't continue to use that. If it's hydrogen and methanol in the hydrates, and wood is here, and metal hydrate is this corner. And of course, there's a liquid hydrogen tank here. So this is the passenger car. You can see compared to, this is the 200 bar at the time. Of course, now 700 bar, you can probably reduce slightly between this volume. Therefore, it's viable for a passenger car if you use 700 bar. So the liquid hydrogen, because of the cryogenic liquefaction, is very energy intensive. And also, during handling, the loss of hydrogen by evaporation is quite high. So therefore, the overall calculation is 1/3 of the energy will be lost. So only for very niche applications, we use liquefied hydrogen. I think in the space shuttles, in the old days, you use liquid hydrogen. Chemical hydride system suffer from the weight and cost concerns. And this is the chemical hydride. This is a typical conventional one. And this is something that I will talk about in a minute. The US DOE also has a roadmap for, this is a more recent roadmap for hydrogen storage infrastructure in terms of the system capacity, in terms of the system cost, storage cost, and then the kinetics, the charging and discharge time required. But on the left, you can see the different state. Okay, compressed hydrogen gas illustrated here, and the liquefied hydrogen. And then here are the different state of absorbed or chemical bonded hydrogen in solid materials. You can generally call adsorbent, right, or catalyst. So that's the illustration. But the US DOE's target is approximately 5.5% by weight, and by system volumetric capacity, there's a specification. The cost, $300. So this is not really big, but so far, no one has commercially met the DOE target. So far, this is the year, 2025. Right, charging and discharging, of course, should be comparable to the refueling you go to a petrol station, right? So within a few minutes, 3 to 5 minutes, preferably 3 minutes. The IEA benchmarks 5%, that's a great metric. And practically, they have to be within a few minutes. You know, the IEA defined as less than 5 minutes, which is similar. So we have been working on this for a while. And in fact, we stopped. Now someone else picking up, I think, made a huge progress. So we published this paper almost 20 years ago. And we have subsequently patented this. So the catalyzed, this is a magnesium hydride, which is quite conventional hydride. It's metal hydride. Metal hydride give you the good kinetics, good volumetric density, and also very cost efficient. It's very cheap to make magnesium or lanthanum nickel 5. So the catalyst plays a role to enhance the kinetics, as we all know. Therefore, we achieved at that time, 20 years ago, almost 20 years ago. So with this, at that time was the IEA target we met, and then DOE target is still some gap. So that is the vanadium, titanium, and with a bit of a carbon nanotubes, 0.001%. Carbon nanotubes actually play a significant role. We can get to 5.2% by weight, but 15 minutes. So that's still some gap between the DOE target and then that result at the time. So, however, I was very pleased to meet Professor Zhou Jianxin, who's from Shanghai Jiao Tong University, just last year. So he came to visit Surrey. He said, "Max, did you know that we learned so much from your paper? Now we commercialize it." So Shanghai Jiao Tong produced the first multi-ton storage using magnesium hydride. And of course, he doesn't want to tell me what catalyst they use. He said, we use a different catalyst from what your paper used. But nonetheless, very pleased because we actually licensed our origin technology to Hydroxia, and they actually bought Hydroxia. The company they spin out in Shanghai Jiao Tong, they bought called Fusan, bought Hydroxia. You can see this is their demonstration on a big truck with Hydroxia's name on it. And they achieved 7.6% at low pressure and low temperature, ambient temperature. The system can actually absorb 900 kilogram of hydrogen. This is a lot of hydrogen. And the predominant use for this will be shipping. You know, Shanghai Jiao Tong is also very top institution, which actually specialize in shipbuilding. So this is a perfect combination of that kind of application. Now, shipping is going to be the biggest sector in terms of hydrogen in the next couple of decades, because shipping consumes so much fossil fuel at the moment, and you use so much energy, and then the marine pollution is really, really serious. Right, I think they won a big award at the IEA Hydrogen Conference Award last year. Gave Professor Ding Wenjiang and him. Ding Wenjiang is an academician in Shanghai Jiao Tong, and him who pick up the award for this commercialization, which is fantastic. So we stopped doing research in this area for quite a number of years, but I think it's great to see how this field is evolving, becoming more commercial, viable. However, just last few slides, 2 slides to just summarize the hydrogen storage, where this will go in the future, right? So I actually like this, even though this is an old review paper. So if you look at the various systems from the conventional hydrides, like the magnesium hydride I talked about, to complex hydride, to sorbent systems, the MO5, MOF5, and many other physics option-based systems, and chemical hydrides. So in terms of the red, yellow, green, for the various technical parameters, from volume, gravimetric capacity, to reversibility, the thermodynamics, which is the energy required, and then kinetics, charging, discharging, time, and efficiency. The conventional hydride is probably the best still, right? The kinetics, the gravimetric density will limit it, the long range. You can't have, long range application. However, the chemical complex, the more complex hydrides, the kinetics is actually the burden. So, but you have to improve the kinetics by using catalyst. So these two systems, a lot of people are trying to commercialize, right? And in the future, of course, there's many studies and still ongoing trying to search for the optimal hydrogen storage materials, including then Professor Xiang Dongyao is my former postdoc, who's now in Zhongshan Sanyeshan University in Shenzhen. He's the dean there. He actually did a review a few years ago and look at the mechanistically, what are the virgin sort of land, where's the most productive in terms of optimizing the hydrogen storage. So he pointed out, actually look at the molecular absorption as a cluster. So this is the mechanism. So like MOF bimetallic complexes is the way for the future. So lots of articles and research papers now is coming out in this area. Right, let me finish. Having talked about the hydrogen production using nanomaterials and in fact functional materials involved in hydrogen production, and in terms of the storage materials as talked about. But for us as a scientists and engineers, why we do such research? What do we want to achieve for society? So I often ask my students and postdocs to think about this question. We want to make a difference, the impact to industry, to the economy, and to society, right? So in order to do that, many of our students got actually lost in the trees, not seeing the woods, not seeing the big picture. So how to take, a market-driven approach or societal needs approach. So this is what we should learn from the carbon fiber, the carbon composite industry that started from the 70s and then gradually commercialized using this approach here, right? So you can see that the situation, the market needs, very clear. Then you look at all the properties as we study materials, and then from systems approach, and then to materials, atomic, mechanistic approach. Then you go in the loop, iteration, trying to optimize. Then eventually, you can get the materials perfected and to be applied on a commercial scale. So this is also something that we should learn in functional materials. So whether it's catalyst or electrode, adsorbents or storage materials. So this is something that we should always keep in mind from the mega trend of the society. What is actually happening in the world? I mean, then if you talk about the geopolitics influencing policy, policy influencing funding, then industry, trade, production. The whole confluence of those factors determine the megatrend. The megatrend determines what society needs. And the societal needs will determine the markets. And then from that, you see, okay, what do I need to improve in terms of the system performance, device performance? And then you go down to the materials. This is something that, is just the other way around, because many of our students, me included, when I started to do research, I look at what's hot, what's the frontier in terms of the the knowledge, right? And you're not keeping in mind of the bigger picture. Therefore, sometimes you get lost into, oh, this is fantastic material, looks beautiful, but what's the use? Nothing, right? So let me finish with my gratitude to Professor Chen, to Hong Kong Poly for this fantastic opportunity. And now, thank you very much for your attention.
Professor Lu gave a very inspiring and clear lecture. And I didn't realize you have published so much as a president of a university. This is really amazing
Past tense.
achievement. But it's all a pioneering work, right?
Thank you.
It's very impressive to learn that Shanghai Jiao Tong University could, based on your research, and make this into reality. This is a wonderful achievement. Now we like to open the floor for discussion. You have a microphone just in front of you. Just push on, and you can ask questions. Yes, please.
I'm very glad to know that there is indeed the possibility to use hydrogen in the shipping industry. I'm a diver, and I know very well how polluting ships are, both in terms of the discharge and also the fuel that they're using. In fact, this is one of the weak areas in decarbonizing energy use. So you are the expert here. So for how many years we need to wait before most of the ships? It may not be too possible to have all the ships, because some are really very small, and I'm not too sure if they are serviced by adequate facilities to use hydrogen, and also do they have any incentives to change the engines of their boat from the current one to the new one? This is another big question. Okay, so what's the time horizon that you have in mind? Can we actually meet that 2050 deadline for decarbonization for the shipping industry? This is my first question. And also the second is, what about the aviation industry? Can hydrogens be used in that industry as well?
Yeah, I think it all depends on how the investment, the costs, but technologically, because the Shanghai Jiao Tong produced the first tonnage based storage, solid storage materials, and it's demonstrated the technical feasibility. And I think in the next 5 years, there will be a lot of companies going to develop this, roll out in the shipping as a pilot. So I would say, in my view, if all the investment and also legislation are in place, 10 years from now, you see the shipping industry will change very rapidly. Aviation industry is the same. Aviation industry, in fact, there's a cross-Atlantic flight. It's a British company using hydrogen. It's called the Air Zero flight. In one of my slides, I show the airplane. But it's small aircraft still, not the commercial jets yet. But I think they are moving very fast because the requirement is getting more stringent, in particular Europe. But in America, it's difficult to say because there's a rollback. The policy is changing. So it all depends how this. I would say 2050. Definitely, hydrogen will become quite dominant. Maybe 30 or 40% of the carrier will be hydrogen. And of course, you never change the energy mix completely overnight because the infrastructure will take decades to replace. Django. And
okay, thanks very much for the very nice talk and very, I think, give us a hope how to use hydrogen and for transportation vehicles. You mentioned about the Shanghai Jiao Tong University developed the the technique use magnesium to
Hydride, yeah.
store hydrogen. It's about 14 kilos magnesium store 1 kilo hydrogen, which is very, very promising.
Yeah.
If I drive a car, for example, if you use a car for 500 kilo,
No, you use
right,
a 5 kilogram
right,
hydrogen
about
only, yes.
5 kilos and about 70 kilos of the casing of magnesium.
And it's only 2 atmosphere
Okay,
maximum,
okay.
but they use actually near ambient pressure,
Okay.
which is also very promising. Very,
Okay,
very good. Yeah.
probably this is, if I estimate this with the electric cars now, is much, it's much lighter. If you talk about this, it's much lighter and very promising. Do you know what's the price on this? Another factor is the price.
Okay. I think the price, the US DOE target is about $1,000 for the storage system.
Yes.
I think that we're still looking at double that,
Mm-hmm.
at least $3,000 for that storage system.
Okay.
But don't forget, when you use hydrogen stored, whether compressed or absorbed in the solid material, you need fuel cell as well. Fuel cell cost is still very high.
Okay.
So this is another part of the equation.
Another factor.
Yeah.
Yes. Yes. Yeah, that's right. But give us a hope on this.
Yeah, I mean, there's a lot
Give us
of
a
demonstration. I know buses in London and many,
hope.
in fact, in I think the Winter Olympics. There was
But they mainly use the gas storage.
No,
70 bar
no,
or
hydrogen.
100.
It's
Or,
hydrogen.
Yes,
Okay.
use the gas with the hydrogen in gas form.
The former minister of Science Technology, Wang Gang, I know him very
Yes,
well.
and in
So
gas
he
form,
does
I
a
must say.
lot
Yes,
of demonstration in China.
Mhm.
And there's also government subsidy for hydrogen
Yes.
fueled cars now.
Yes, but the hydrogen in the gas form, what I say.
In the gas form.
In gas form,
Yeah,
and
yeah.
with the 70
Compressed.
bar, compressed
Not
gas.
700 bar, I think.
Right,
Demonstration they
35
use for-
35 and
Yeah,
70,
yeah.
two standards.
Yeah,
Yes.
yeah.
Thank you.
Good. And Professor Yu there.
Max, really enjoy your talk as always. I have a simple question about the safety of carrying a tank of hydrogen in your car. You said it's like carrying a bomb, but
That's public perception, not real.
yeah, it's a wrong perception, I think. Yeah, we do that with LPG. We have taxis carrying LPG, and I don't think we have huge problem with that. So why is there such a concern with hydrogen?
I think it's a wrong perception the public has, because the high pressure and the hydrogen, the two words add together, psychologically, people say, oh, it's going to be a bomb. As we know, hydrogen is LPG, that's for sure. However, I think Jerry is the expert in this area. If you look at the hydrogen, how we handle hydrogen, chemical industries, we have no problem. Very few to hydrogen explosion, because the hydrogen explosion limit is actually right. So you have to have it right in the middle of the range. If it's too low, won't explode. If it's too high, wouldn't explode. So but it's a public perception mainly. But to convince people to drive a hydrogen car which is compressed at 700 bar. I talked to many people say, I wouldn't drive such a car. But even autonomous vehicles, people wouldn't want to drive autonomous vehicles, wouldn't want to sit inside, because they say, oh, I lose my control because I put my hands on the wheel, because that's how I used to drive and have the sensation. And people say, oh, never use a autonomous vehicles. Perception is very difficult to change.
Yeah, thank you.
Oh, this one.
Okay. Hey, Prof. Chen here. I might ask two questions from a layman point of view, not technology point of view. Compared to solar energy and hydrogen energy, what's the advantage, disadvantage for future? That's first question. Second question, after 50 years, 100 years, our energy will get more or getting less? When the large language model said they use a lot of energy, can we survive? So that's two questions from layman point of view.
or not layman, you are the expert on AI. So, you know, AI does cause a sort of energy issue, the demand issue. Let me answer the first question. I think solar to hydrogen. What's solar energy? The sun is a nuclear fusion reactor. It is up there free, right? So therefore, the holy grail is to convert the solar energy from the sun radiation on the surface of the Earth directly to, of course, now we convert to electricity. Then you have the efficiency, let's say, capped at 30%, the PV, and 70% you're not converting. And you can actually then convert electricity or store electricity in storage and then convert it back. You also have some losses. But the different application scenarios are as well. So I think you can hear me, right? Okay, thank you. It's me, probably. Yeah. So I guess the solar to hydrogen or solar to X field, whatever the purpose, is actually a dream. For many scientists, engineers, we should look at how directly utilize the solar energy without the intermediate. I think your last question is to do with, you know, large language model and whether we have enough supply of energy, right? I think in the future, will have to be a mixture of solar or wind, the renewable energies, with the nuclear in order to really meet the energy demand. In the era of AI, even though DeepSeek is demonstrated you can use much less energy resources to train the model, but still, as everyone starts to use DeepSeek, and the energy demand is huge, therefore, you have to consider a mixture of clean energy, such as nuclear, and also renewable energy. Well, I think nuclear technology, you know, probably expert here, I'm not expert. I think there will be safe nuclear energy, the 4th generation, even nuclear fusion is possible. Chinese scientists making lots of progress in this area. Maybe 50 years from now, not 100 years, I think the humanity will not have an energy problem if you have this combination. And whatever model you come up, computer scientists, very clever, come up, there will be energy, enough energy for you. Well, I'm optimistic.
Okay, yeah, go ahead.
Professor, thank you for your sharing. I don't have any problem to create large amount of hydrogen. I am partner in the patent. We have know how to create a lot of hydrogen easily. But the problem for past 20-some years, I'm not a chemical engineer, but I know that we can produce a large of hydrogens simply. But how to storage it and transform it and then make use of it for other energy utilization. The problem is when we create all the hydrogen, it is in gas form, very high temperature. And so we have to use the thermal exchange to cool down it. And also we have to transfer it to the usage. When we produce all the hydrogens, we also produce a CH4 because we use plasma technology. This is my patent. And this is, I think, is the fastest and the largest scale that I can imagine. I know that we can create hydrogen faster for whatever technology I've come across, simply. But the problem is, for many, many years, if we have to create this, we have to separate the hydrogen and the CH4 and other syngas. Simply, some wise men told me that we use a to separate it easily. But once we separate it, the 6,4, we can sell it as a natural gas and some people do it. But the hydrogens, if it is not for industrial purpose, to create other, no matter it's medical, whatever they use, then we have to burn it. But once we burn it, the combustion is great. But the best way is to storage it and deliver in the right place to use it. We can create it anywhere in the world, including the land or marine, or whatever. But of course, it is how the motor engine to cope with it. Because
I get what you mean.
I just want to ask where I should approach, who I should approach to find a team who can match with me. And then I want to further develop the utilization. Can you advise?
Okay, so I think you talked a number of points there. I think first and foremost, you were saying production is not a problem. Production is a problem in terms of cost. In terms of you talking about, plasma assisted, hydrocarbon cracking or reforming. Well, that's still fossil fuel based, and that's called gray hydrogen if you produce that. And if you then look up the carbon, capture carbon, sequester carbon, because even methane has a carbon in it. So that's a problem. So the overall cost is actually a problem. And you can't produce, now the whole world is only 1 million tons hydrogen produced, right? And this is only about, less than 1% of the energy mixture. So production is a problem, but you're quite right. Storage and transportation is a problem. That's why what I talked about. And where to find the talent? I think China and of course Hong Kong has a lot of talent. If you have the good ideas, get funded and get the talent, you can carry on to solve some of the problems I talked about, right?
Okay, I do have a question for you.
Sure.
You mentioned about this conversion efficiency, right? Now it's about 10%. And then you will compare
Use solar to
hydrogen.
It's actually less than 10%.
Yeah, let's say assume 10%. But if I use PV panels, I can convert it into electricity, which is much easier for transportation, for storage. Maybe not the storage, but transportation, right? It's about above 20%. So what is the bottleneck for this conversion, the efficiency? Is it because of the catalyst or whatever?
Yeah, very good question. I think the bottleneck is the photocatalyst, is the conversion efficiency, the photon energy that actually hit the surface of the catalyst. If you can convert, more than 10%, it becomes viable. I think your calculation is right. 30% times 70%, it gives you 20%. So that's the PV to hydrolysis.
Yeah.
The problem with electricity, why, you would argue, why not just stick to our lithium-ion battery, electrical vehicles? I think the systems are different. In terms of the driving range, even the solid state lithium-ion batteries now claim can go 1,000 kilometers, right? Charging, I think BYD just announced about 5 minutes charge 500 kilometers driving range, and then maybe 10 minutes or maybe a bit longer than 10 minutes can charge 1,000 kilometers. But fuel cell hydrogen cars can go much, much longer range. That's one. Secondly, fuel cells don't use lithium. Lithium is a critical mineral. It's very limited. Right. I think there's some calculation, some economists who work with metallurgists in Japan, they calculated the availability of lithium is only enough for 40%. If they all mined economically, for 40% of the whole world's electric vehicle, what about the 60%? So that's a bottleneck. Unless you come up with the aluminum air or the new generation of batteries, and also economically, which give you the long driving range or a large capacity for stationary storage, electrical storage is still limited, right? Limited use or limited by resources. Therefore, I think hydrogen has the promise if you can crack some of the technology bottleneck, like hydrogen storage.
Yes. Yeah, I remember the Japanese really put a great effort in the hydrogen car.
Oh,
right?
yeah, they did. Honda
Yes.
and
then-
Toyota.
Yeah.
Yeah.
But I think what's the problem? Why they not become so popular?
So the fuel cell cars, I think when we were doing research, was very promising. Why we stopped the hydrogen storage? Because no funding. Because the whole industry stopped developing fuel cell car because the cost of electric vehicles is much cheaper than the fuel cell vehicles because the fuel cell itself. Fuel cell is the engine, right?
Yes.
So that's the problem. But now, recent years, people realize that now, Toyota, Honda, many car manufacturers start to have more research investment in fuel cell and hydrogen now because it's come back again. So after almost 20 years.
Okay. Well, that's great. Thank you. Yes. Question there.
Hi.
Yeah, thank you very much, Professor Liu. A very impressive talk. Actually, I'm from the industry. I'm an industry guy. And in my company, we're also using a lot of hydrogen, in the furnaces. Yes, which is very expensive, of course. So in parallel, we're thinking about other ways instead of hydrogen. So the hottest topic is electrification, which means we use electricity directly in our furnaces, in our processes, instead of using fossil fuels or hydrogen. So I just want your opinion about the biggest competitor for hydrogen and any comments on the competition. Because a good example you just gave us is about the cars. Now we talk about more about electric cars instead of hydrogen cars. So what is the biggest competitor for hydrogen?
The biggest competitor is the electricity. That's no doubt at the moment. Of course, electrical cars or electrification of metallurgy industry or other industries. However, depending on your system analysis, what is the holistic, so-called cradle to grave analysis, the life cycle analysis, right? So electricity, if you look at that way, is also not, the cleanest, right? Depending on what's the energy source to generate electricity. So I'm not the expert to comment on metallurgy because even though my bachelor degree was in metallurgy, but I forgot about all the furnaces. The Baowu still uses, but you actually making a lot of progress. Hydrogen for smelting has a lot of advantage, even though you say cost is still high. That's because the hydrogen production is high. If you reduce the hydrogen produced from electrolysis by a factor of 3, from $6 to $2. So that's the benchmark for industry. For vehicles, for stationary industrial process become very, very viable. And therefore, your cost in terms of the energy input for smelting would reduce, may not be proportionally, maybe quite significantly. I don't know how much. So that's my only observation on that. But the future, I think, has topics, as I said earlier, to answer the other question.
Yeah, thank you.
Yes, please, Professor Meng.
Yeah, Professor Mike.
Professor Liu, I missed your most important part during the talk. I just came in an hour ago, and interesting to hear all this discussion. Questions. I understand there's a company in Hong Kong called Tang Gas. They produce all the gas for the Hong Kong family, and they are now doing production of gray hydrogen from the methane and all this fuel gas.
Yeah.
Now the question is, after they produce the hydrogen, how do they supply to the the station. Actually, at the moment, we are thinking that in the future, all the petrol station will be converted into either electricity supply or hydrogen supply, right? The interesting thing is how they supply those oxygen through the existing pipes, or they have to lay extra pipes, because the existing gas pipes is a little bit too old. I mean, in all big cities, we are having bombs along our main streets because of these old pipes now.
Yeah.
So in the future, if we have hydrogen pipes, we are creating another bombs in our high streets. So any companies or any countries are doing research on this supply of hydrogen to the pumps, to the petrol pumps stations,
Using existing natural gas pipes.
or whatever pipes. Yeah.
There are many countries doing demonstrations, but not commercial deployment yet. I think in theory, we all know the chemical industry handle hydrogen and plants from one section to another section of the, not without any problem. We're using natural gas pipes, right? However, if you have the tongue gas pipes, that is maybe 100 years old, that's pretty dangerous, because hydrogen can embrittle steel and can cause cracks, and therefore leakage or maybe explosion. So as you mentioned. So therefore, you have to really take into account the safety of mass distribution using existing infrastructure. And building a new infrastructure is a possibility, but cost again. So the initial capital, outlay is big. But the storage means that I talked about, compressed tanks, I think is only perception, is not safe, but it's actually very safe, right? You can distribute that. You can then rely on the solid material if we, really see the tonnage production at a very low cost, the Shanghai Jiaotong's new products. So hydrogen iodide with the catalyst. So that's another way you can see that, well, in the future, you can make this absorbent as a canister, just a plug in, plug out, right? So within about 30 seconds, you replace that, and the hydrogen distribution will be just selling cartridges, right? So that's one way for vehicles, even for home use, right? Because the pressure is so low and the storage capacity is high enough. And if the materials is cheap enough, I know magnesium is very cheap. I think many experts in this area. So in magnesium, a light metal, making a hydrate is cheap. So I see that there's multiple options, and at the end of the day is commercial decision. That's why my last slide, actually, I talk about, the societal needs and then market forces. When we want to make a difference, we have to work with people like Mr. Ma, from Bao Steel, from other industries, because they are in the business of making products and delivering value to customers, right? So only through collaborating with these people, the business people, we can understand what is commercially viable or not. Because as scientists, engineers, we should be cognizant, aware of these things, but we should seek collaborators to make a real product, to make a difference.
Okay, we have time for last question. Anyone wanted to ask about last question? So if not, I'd like to give another round of applause to Professor Lu for a wonderful lecture.
Thank you.
Yes. So to express the appreciation from PolyU Academy for interdisciplinary research, we make a plaque for you. Yeah, I'd like also to thank all the people here for attending today's lecture, and especially for those who ask questions. PAIR conducted this distinguished lecture series almost about once a month. So our next lecture will be at 10:30 a.m. on Friday, June 13th. and they will be given by Professor Gao Huajian. Professor Gao Huajian is a professor from Tsinghua University, who is an academician for 7 reputable national academies. So it's a very famous person on the mechanics. So I will welcome you to the next lecture. Thank you very much. So this lecture is adjourned. Thank you.